So here we go. Good morning, good afternoon, good night to all of you, and thanks for attending this webinar of the Technical Talks of CTSoc series. Um, I'm Fabrizio Lamberti. I'm the Vice President of Technical Activities of IEEE Consumer Technology Society, and I will just provide you with a brief introduction to this Technical Talks series within the context of CTSocs and its technical activities area. So, technical activities areas has been launched at the end of 2020, and it includes the technical committees and the future directions committee. Basically, CTSoc has identified over time 15 technical committees which are representing the various areas and fields of interest of consumer electronics and consumer technology domain. As you see here, we have a number of topics included, and today we will listen to the speeches of two colleagues working in two of these areas, which are the CCN, Consumer Communication Networks and Connectivity, and the SMC, Application-Specific Consumer Electronics for Smart Cities. Basically, this is the organization of the technical activities area, which has a chair, which has these 15 technical committees, each one with its own chair, co-chair, and vice chair. And they constitute the technical committees board, which includes also the vice chair, Dixon Lin, who is attending today, the president of CTSoc, the VPs of conferences, publications, industry and standard activities, and of course, the VP of technical activities, so myself. Here you have a list of the officers of the technical committees, and today I have to thank the officers of the CCN and SMCTC for having identified our two great speakers. Each technical committee has its own page under the technical activities tab of the CTSoc website, with its mission, with the officers, with a list of members, and with a number of license positions. They are organizing periodic meetings with their members. And if you are not a member yet, you can go on this page, or you can follow the QR code, and you can fill in the technical activities membership application form. And note that you can be a member of a technical committee without actually being an IEEE or an IEEE CTSoc member. So the community is larger than that of the members. Actually, we have so far 1,500 members which are covering the various areas that I introduced. And what's the reason for being a member of one technical committee? So the technical committees are supposed to be the backbone of all the areas of CTSoc behind the activities of CTSoc, like conferences, like publications, standard education and history. They are supposed to investigate, evaluate, promulgate, and foster the emerging and current technologies and applications of interest to CTSoc. They are expected to be involved in the launch and organization of all the initiative regarding the above areas. Just to provide you some examples, it is from the technical committees that we appoint technical positions in conferences. It is from the technical committees that we identify associate editor positions for our publications, the transactions on computer electronics and the magazine. It is from the technical committees that we accept special sessions in proposals in journal and workshop special sessions in conferences. The members of our technical committees are involved in a number of other trans and cross societies initiatives within and outside IEEE, like the IEEE Digital Reality or the IEEE Digital Privacy Initiative. The technical committees are launching special interest groups. They are involved in projects, funded projects like internships. They are involved in the development and implementations of standards. They are those who basically feed the pool of distinguished lecturers, etc., etc. So there are many reasons for being in a technical committee. So I recommend you to join and ask you to solicit your colleagues to do the same, if not members yet. Just let me use this couple of slides to introduce some opportunities which are open to you, to your colleagues, and to not necessarily to members. These are conferences which have open call for papers. They are organized by CTSoc. They are flagship CTSoc conferences or conferences organized together with other society like ICIR in Pisa or ICC Taiwan and ICC Berlin in July and September, or the GCC, the Global Conference on Consumer Electronics in Kobe, late in October. And let me mention also the opportunities regarding the journals. So these are the two flagship journals publications of CTSoc, the Transactions on Consumer Electronics, and the IEEE Consumer Electronic Magazine. So they have calls open for the magazine in particular. I'm serving as editor-in-chief for the magazines starting January 2026. So these are the open call for papers in special issues. So in case you're interested, and in any case, if you know someone who could be interested, please feel free to share these opportunities. Coming to the technical talks, so the technical talks have been launched within a single or within individual technical committees, and then they have been escalated as an initiative involving multiple TCs. And the idea is to have every time a couple of speakers representing two different TCs, because we think that from the diversity, the great ideas can come out. And we have had already more than 20 talks. The next one will be on April 29, same time. Well, actually, same time, 2 p.m. Italy or Central European Standard Time, because there will be a time change in this weekend. Today, we are lucky because we have two great speakers representing TUV, CUD, Auto Service GmbH Germany, and representing Keist AI from Korea. So let me, of course, welcome our speakers. Welcome again and thank them for being with us today. I'm going to leave the floor to the officers of the two TCs to introduce their speakers. They will give a speech for about 15 and 20 minutes, and then we'll have time for Q&As. Thanks again.
Okay. I'm
Yeah.
very pleased to introduce our invited speaker named Dr. Kang Eun-jeon. Kang Eun-jeon is an expert in efficient AI and sustainable IoT. And currently, he is conducting research at the KAIST AI Center. And he graduated HKUST. And his work bridges the gap between hardware efficiency and machine learning performance. So particularly in the realm of in-memory computing and edge AI. Today, he will give a talk about towards flexible and adaptive AI models for sustainable edge intelligence.
Thank you. So Chang, we might have discussed about the change in the order of speakers. So if Dr. Kang is fine, we can continue with him, and then we will pass to the other speaker.
Yeah.
Okay. Thank you very much. You can share your screen if you like.
Oh.
Dr. Kang Hyun?
Oh,
Okay,
okay, okay.
please.
Yeah, sure.
Okay.
1 second. Uh, okay. Um, yeah. Can you guys all see my screen?
Yep.
Okay,
Yep.
awesome.
Okay. Yes.
Okay, let me begin. So, firstly, thank you for having me, Professor Fabrizio, and also Professor Suchang. It's my pleasure to give a talk on one of my latest research topic, which is titled "Towards Flexible and Adaptive AI Models for Sustainable Edge Intelligence." I believe building a lightweight and compressed AI model is of is a very important topic and also of interest to the consumer electronic community, mainly because our consumer devices are limited in memory, compute, and power. So I will go ahead and share some of my latest work and and before we begin, let me briefly introduce myself. So my name is Kang. You guys can just call me Kang. I was born in Seoul, South Korea, and I spent 9 years in Europe doing my primary and secondary education. And then for my bachelor's education, I moved to HKUST, where I did my Bachelor of Engineering in Electronic Engineering and also my PhD. After that, I returned back to Korea to perform my military duty. So I was a postdoc at Sungkyunkwan University, which is one of the oldest university in Asia, about like 600 years old. And now I've repositioned to KAIST AI, and here I'm focusing more on research of efficient AI and also physical AI. Okay, to set the stage. So AI has taken the world by a storm, and they've been showing a huge improvement in performance that's basically revolutionizing how we work and our lifestyle as well. But all of this performance is coming with this trade-off that AI models are growing in size at a very fast rate and also in cost. And this causes a mismatch in AI compute supply and also the model requirement. So here we have a graph showing how the model size has been has been evolving over the years. So this red curve is showing how our transformer models parameter count has been increasing, and this green curve is showing how our AI hardware memory have been increasing. So here we can see that there's a huge gap in what our transformer models require in terms of the memory, but what our actual hardware can provide. So you can actually see that transformer size have been increasing by 410 times every 2 years versus our AI hardware memory have been increasing by 2 times every 2 years. And note that this y-axis is actually in log scale, so the gap is very, very huge. So the memory is the major bottleneck in AI acceleration. So how do we solve this problem? So there are two ways we can solve this. The first direction is just building a smaller AI models through techniques such as model compression. So we basically want to make a larger model that consumes higher memory and higher compute into a smaller model that consumes lower memory and lower compute. So one very widely adopted technique to achieve this is quantization. The key idea of quantization is that you take the model parameter of this larger model, which is generally stored in floating point number format, either in FP32 or FP16, and then you quantize it. You reduce this numerical precision into a integer 4 precision or integer 8 precision, which will consume only 4-bit or 8-bit. FP32 will cost 32-bit. By doing so, we can reduce the memory and computational complexity at the same time. And now a more advanced version of this quantization is a flexible and adaptive compression or flexible and adaptive quantization. And this is one of the research topics that I've been focusing on. And the key idea here is that instead of quantizing our model into a fixed precision, say 4-bit, we want to adapt the quantization precision of our AI model to adapt with varying hardware constraints or vary it with different task difficulties. Because a lot of the tasks that we give to our AI models are not necessarily always difficult. For example, if we put our agent to perform certain tasks, it will probably struggle a lot in the planning stages, but during the execution stages, the task will be a lot easier. So we can vary the precision there to modulate the computational complexity, saving some energy and saving some memory. Now, another direction of research that I'm focusing on is emerging computing platform for AI. So in case of von Neumann architecture, it is struggling a lot because our AI models are too big and data bus bandwidth turned out to be insufficient to support these AI models. So I also explored this new AI computing platform called analog and memory computing, where the computation is performed directly inside the memory, removing that requirement to transmit our very large model weight parameter between the CPU or the GPU and the memory unit. So here's a general overview of my research. So my research is divided into two directions. Along the software axis, I am working to develop new flexible and adaptive compression techniques, mainly focusing on quantization. Along the hardware direction, I am investigating these new computing substrate called analog and memory computing. And also, I'm doing some software and hardware co-design, trying to reflect our AI model requirement into the hardware design, and then reflect our hardware constraint into our AI model design and how we compress these AI models. But today, we are just going to focus on the software side of my research. Okay, so let's talk about flexible quantization. So quantization makes AI more affordable. So here is a quick example to show you guys how that works. So serving a 175 billion GPT-3 model at least requires 350 gigabytes of memory in FP16 format, which means that you will need at least 800 GPUs. But if we were to quantize this model into int8, it would only require 175 gigabytes of memory, which can fit in roughly 800 GPUs. Quantization does really help to make AI more accessible. But what are the shortcomings of the existing quantization techniques? So the main issue is that they lack the spatial and temporal flexibility. So a lot of the quantization techniques that we use are uniform quantization, which means that every layer in a AI model is quantized to the exact same precision. However, we find that this is actually not the optimal solution for two reasons. Firstly, each individual layers, they may have different sensitivity to the quantization error, or they may have different importance. Hence, it is actually necessary that we allocate different precision to different layers, varying depending on how they vary in terms of the importance. So we investigate how to approach this mixed precision quantization, where we vary the precision flexibly across the spatial domain, across different layers. Now, the second issue is the temporal flexibility. As I mentioned, as I hinted briefly before, not every input or not every task is of the same difficulty. Some tasks are more easier than the other ones, and some tasks are more difficult. To that end, it would be actually much more efficient if we could vary the computational complexity or vary the precision of our AI model depending on those task difficulty. But there are two key challenges with approaching these mixed precision quantization and multi-precision quantization techniques. Now, the two challenges are that first, the training cost of such flexible models are very high. So how to train these models more efficiently is one of the challenge. And the second challenge is that even if we were to build these mixed precision and multi-precision quantization models, they often cannot be accelerated in inference time. They are not giving that tangible speed up. So that is another issue that we try to resolve. So here's an overview of how we are going to of the papers that we are going to discuss today briefly. So first, we're going to go through this paper called EMQNet, which was published in New York 25. Here in this work, we tackle how to train those multi-bit precision network or those temporally flexible networks more efficiently. And next, we're going to talk about this paper called TrunkQuant, which was all about how to accelerate this efficiently trained flexible networks to actually load it onto like embedded systems and accelerate their inference. And next, we are going to talk about this paper called MSQ, which was published in ICCV 25, which is about how to efficiently train a mixed precision network. And of course, we have some ongoing work on how to accelerate the inference of the mixed precision networks, but this work is still a work in progress and still under review, so we are not going to discuss this paper for today. Okay, so let's talk about our first paper, which is EMQNet. And before we talk about this paper, let me provide a brief background about multi-bit precision networks. So multi-bit precision network is composed of two components. The first one is the parent model, which is FP30, which is composed of the FP32 weight shared by all the child models. And the child models are the actual quantized model, which are generated by quantizing this FP32 parent model. So from a single parent model, we can quantize that parent model to generate the 1-bit child model or the 2-bit child model, and so on and so forth. And the reason we want to do this is twofold. First, either we want to have an efficient deployment to a diverse set of edge devices without additional training. So for example, like a smartwatch will have different memory availability than this smartphone, and the smartphone will have different memory availability from this cloud. So we should deploy a different type of model to all of these devices. So by using this kind of multi-bit precision network, we can have this efficient deployment across different hardware that has different hardware constraints. And the second reason we want to do this is really because of what I mentioned before. We want to adapt to varying task difficulty. Now, but training these kind of multi-bit precision network is very costly because it requires multiple forward and backward propagation. So the essence is to train this parent model, we first train a 1-bit child model, and then we train the 2nd-bit child model, and so on and so forth, such that we find a local optima that will make all of these child models happy. So that's basically how we train a multi-bit precision network. And you guys can see that this will be very, very costly because we need so many forward and backward propagations. To address this issue, we propose this technique called core set sampling and batch norm optimization. So previously, we were training these child models with the entire full data set. But our key idea was that we don't need to actually use the full data set. We can actually sample a very small proportion of the full data set and then train our child models on those subsets. And our key observation was that because all of these child models are sharing the same parent model, even if we train our 8-bit child model with a smaller subset of the data set, our 4-bit child model will also benefit from this 8-bit child model training because they're all sharing the same parent model. So our parent model is kind of acting as a conduit to transfer the training signal between different child models. So that was our key observation, and we also verified this empirically by measuring the gradient generated by different child models for different subset. And we can see this plot is basically showing that, and we can see that for different layers and for different child models, these gradients are pretty well aligned, which means that they are sharing that training signals. So we've experimented this on various image classification networks such as ResNet and vision transformer models using ImageNet 1K. And we were able to prune away 80% of the data set. That means each child model is being trained with only 20% of the data set. And we actually achieve almost negligible amount of accuracy drop while achieving up to like 6 times model training speed up. And and because our method is so efficient, we were actually the first one to apply such multi-bit precision network training on VIT models. Yeah, so we can see that the accuracy drop is also negligible in these vision transformer models while achieving significant training hour speed up to 2 times or 3 times. Okay, so now we have trained our model, our multi-bit precision model. Now, how do we actually accelerate it on the edge? So one of the issue with these multi-bit precision model is that their parent model is 32-bit. So that means our edge devices need to have this 32-bit model stored in the off-chip global memory, which is large. And then when you want to generate the child model, you have to load this 32-bit model and then apply some quantization function, which will be a floating point operation. And whenever we want to switch between precision, we would have to access this 32-bit parent model every time, which is also very expensive. So to address this issue, we propose a technique called trunk quant, where the idea is that instead of having a 32-bit floating point parent model, we wanted to have an 8-bit integer parent model. And we would load this 8-bit integer parent model and then truncate the LSB to generate the lower precision child model. This means that we have lower memory footprint on our global memory. And also we have less memory access because now we are not accessing a 32-bit model, but just the 8-bit model. And we're using a truncation operation instead of quantization operation, which is much more friendly because truncation operation is an integer operation. Now, but what's the challenge with doing this truncation quantization? Now, the challenge was that we had to design a completely new quantizer to support this quantization via truncation technique. So in the traditional round to nearest quantization technique, we find that there is an issue that this MSBs cannot be shared between precisions. So here is a quick diagram that will illustrate this. So suppose we are trying to quantize a floating point weight that is normalized to value between 0 and 1. And here, these bins are basically showing what the corresponding floating point value will be quantized to. So for example, if our floating point weight is in this range, then it will be quantized to a value, integer value of 001. And if our floating point weight lies in this range, it will be quantized to 001. And if we were quantizing to 2-bit, if our floating point weight is lying in this range, it will be quantized to 00, and so on and so forth. And what we realized is that if our floating point weight is lying in this particular region, we find that the MSB will not be shared. So to better illustrate that, here is a quick example. So suppose our weight, floating point weight has a value of 0.81, which lies right here. When it is quantized to 3 bits, it will lie in this area, having the value of 110. But when it is actually quantized 2-bit, it will be quantized to 10. Notice how their MSBs are not the same. And if we were to quantize our model to 3-bit and truncate the LSB, there will be a discrepancy in the second bit. So what we learned is that using the traditional round to nearest quantizer, quantization via truncation actually causes these errors. And these errors can propagate to break the model performance. Now, to address this issue, we propose a completely new quantizer, which is called trunk quant. And here our key idea was to align all of these quantization bins such that the MSBs can be shared across all the different precisions. And by using this trunk quant, we basically eliminate that error that was caused via truncation. Here we have a quick experimental results showing evaluated on ResNet 20 and ResNet 50. When we are using the traditional any precision approach, when we apply truncation on a 8-bit model, we see that as we truncate to lower bit, the model accuracy will drop very significantly. Versus when we use our trunk quant, even if we truncate to down to 3-bit or 2-bit, we see that our accuracy is well retained. And we also evaluate this on hardware. We find that there's a significant storage saving, and also we simulate our method on an NPU called Iris, and we find that this will not only save the memory requirement, but it will also save the energy required for switching operations. Because here now we are using a truncation operations, which is an integer operation instead of a floating point operation. Okay, let's switch gears a little bit and let's now talk about mixed precision quantization. So mixed precision quantization was traditionally challenging because this is a combinatorial search problem. We have to try different combinations of the precision for different layers, which we often call the bit scheme. And because this is a combinatorial search problem, it was very difficult to find the optimal bit scheme. Now, to address this issue, a technique called bit sparsification quantization was proposed in the literature. The key idea was to split a weight into its bit-specific parameters. So what I mean by that is, suppose there is a weight that can be quantized into 8-bit. Then what they do is they split this parameter into 8 different independent parameters, where each of these parameters are actually representing a bit of this weight. After this bit slicing, we apply L1 regularization on these split bit-specific parameters. And by applying those L1 regularization, we sparsify these bits. And when they are sparse enough, we can just get rid of them. And that actually achieves the same effect as doing the mixed precision quantization. So in a sense, this is actually relaxing this combinatorial problem into a continuous search problem by doing the splitting and applying the L1 regularization on this bit-specific parameters. Now, but the issue with this technique is that to achieve this kind of bit sparsification quantization, you need to split a single weight into 8 different weights. So it will consume a lot more memory to train these kind of networks. Now, to address this issue, we propose a technique called MSQ, which is called memory efficient sparsification quantization. And this is a memory efficient approach to performing this bit sparsification quantization. Now, our key observation was that it wasn't necessary to split the single parameter into 8-bit, because generally it was always the LSB that was being sparsified and getting pruned. So we just had to know the value of this LSB to apply that L1 regularization. So to that end, we simply quantize our weight into, say, 8-bit and, say, 7-bit. And we basically take the difference between these two quantized weights to extract the LSB. And then we apply LSB. We apply the L1 regularization based on this extracted LSB. But what is the challenge here? We find that LSB extraction and regularization also requires a very special quantizer, just like in our trunk quant case. So we find that the traditional round to nearest quantizer failed to extract LSB correctly. So here are some examples of the LSB that's been extracted by taking the difference between the 3-bit and the 2-bit weights. And the problem is very similar to our trunk quant case. It is really because our quantization bins are not well aligned. So we propose a new quantizer called round clamp quantizer, which aligns all of our quantization bins nicely, such that the LSBs can be extracted accurately and also can be used effectively for our L1 regularization. And by doing our MSQ, we can actually reduce the memory required for training these mixed precision quantization networks. And because our MSQ method requires less memory, we can actually use larger batch size, and that will actually lead to a acceleration in training time. So here we see that compared to the traditional methods, we achieve up to like 81% reduction in training time while achieving very competitive and comparable accuracy performance. So here are some accuracy comparison. So we can see that we can compress our ResNet 18 or ResNet 15 networks up to like 11.8 times and 10.89 times while achieving very competitive accuracy performance. And we also evaluate our method on those latest vision transformer networks, and we still find that our method is very, very competitive. Okay, so here is a summary of my talk. So we addressed two key challenges. The first one is efficient training of these AI models, really related to those multi-bit precision models and also the mixed precision models. We also achieve efficient inference, and we are really the first to propose a technique called quantization via truncation, which is very friendly for those edge devices. So what's next? So here we explored achieving spatial and temporal flexibility in AI models, but really focusing on those computer vision models. Now we are expanding our work to target generative models, such as diffusion models and language models. And we are also looking at how we can not just achieve a flexible model, but also build an adaptive model such that we can change the model precision based on the task difficulty or layer-wise sensitivity or token-wise sensitivity. There are some other ongoing works as well. So we are also looking into how to perform mixed precision quantization in conjunction with the latest quantization techniques such as rotation quantization. We are also looking at this very new pruning technique called variance-based pruning, and we are also looking into doing low-rank compression, but doing that dynamically depending on the importance and sensitivity of the input token. Okay, so that's pretty much it. And thank you for listening. And I'm open for questions. And if you guys have LinkedIn, here's my LinkedIn QR code. So feel free to connect with me to stay updated with some of my latest research. Okay, thank you.
Thank you for this very interesting talk. I think we had a talk on a similar topic in the previous or one of the previous webinar. I think it's it's a topic that is getting increasingly hot. So thanks for sharing your research with us. Let me share my screen for a second to introduce. Well, at least to share this slide again and let the officers of the SMC+CCN to introduce our second speaker. ABC,
Okay.
do you want to? Yeah,
Yes.
please.
So can you hear me? Yes. So the second speaker is Mr. Pascal Mas from TUV Auto Service, Germany. The title of his speech is From Vision to Measurements: How the IEEE SustainMobility Framework enable actionable sustainable mobility. Mr. Pascal is actually a senior mobility and automotive technology professional at TVSUD with more than 2 decades of experience across engineering, testing, and operation, as well as management roles. So since 2021, he has served as a director for sustainable technology in the mobility division, focusing on sustainability-driven solutions in the automotive and mobility sectors. Previously, he held leadership positions including head of operation automotive Germany's business lines manager emission and head of emissions laboratories near Stuttgart. He began his career as automotive technology engineer at TUV in year 2000 and has since combined technical expertise with strategic leadership in mobility. So Mr. Pascal Mas, you may proceed.
Thanks, ABC. Thanks for the introduction, Mr. Pascal Mas. Thank you.
Yes.
And the floor is yours.
Thanks for the nice introduction. and I'm going to share this presentation with you. I'm talking about from vision to measurement, how to get a sustained mobility framework enables actionable, sustainable mobility. I do that together. In the past, we prepared that presentation with co-chairs and a core team, and today I'm going to present you the results. I would like to briefly outline the structure of today's presentation. I will start introducing the foundation and the long-term vision of the SustainMobility initiative. Then I would like to go to the motivation behind the initiative, clarify its overall purpose, and introduce the framework, that guidelines to our approach. I would like, as next, to explain the architectural layers of the framework and walk through the key knowledge assets. Finally, I will conclude with the standardization output of the initiative and the overall rationale and why the impact assessment standard is essential to move from an ambition measurement to be comparable, actionable, and to be progress in sustainable mobility. I would like to introduce here the Global Impact Assessment Framework for Sustainable Mobility Systems. It's developed under the leadership of IEEE Standard Association, and the motivation is clear. The transport sector is under an increasing pressure of addressing climate change, urban needs, social equity, economic sustainability, and we would like to have a holistic, transparent, and measurable way to have here success on it. Many sustainability initiatives today focus on a single technology or isolated measures. And in that contrast, we as the framework would like to look to a system-level challenge where technology, society, policy, and human behavior are closely connected. As the core principle, we aligned that initiative on the United Nations Sustainability Goals, the 17 SDGs, as a social enabler to have an efficient solution later on. You can see that the global and the urban scale is in an important role, and today's technical core should provide the context, and the named chairs underline the responsibility and the leadership behind the initiatives. There are much more beside on me. Overall, this message is open to invite people, like we heard also in the beginning. We are not on a single and on a connected or on a already closed organization. We are open, and we would like to share and would like to go together with you to collaborate on a safer, greener, and a more inclusive mobility system worldwide. We started, and that's my first point for that, starting with the vision for 2028. The IEEE Standard Association aims to become a leading international standarding organization, and we would like to offer a family of standards for the holistic sustainability impact assessment framework. The vision is quite broad, based on the 17 sustainability development goals, including safety, security, affordability, accessibility, and social acceptance, and to have a key trade-offs in mobility transition. The work is organized as a collaborative and international multi-stakeholder initiative under IEEE, and we started 2 years ago and are going until 2028 to achieve our goals. The objective is to translate the ambition for a more sustainable mobility to a measurable target. So we aim to attract 3 to 5 new relevant entity members per year to get updated and to find a pragmatic success metric focused on the engagement in the real world relevance. Taking this into account, we would like to offer together the vision, the mission, and the objective at the end shown in a very structured and open, outcome-driven and accountable initiative. This combines then the strategic ambition with a clear governance and defined timelines, and at the end, a measurable result. The activity is set up as an industry connection program. This is the clear and transparent governance for it. And I'm, as the chair, have a co-chair, secretary, and program manager on my side. And it's easy to have access to here. The barrier is quite low. You have an online form, like you also showed Mr. Lamberti at the beginning. So it's also here possible to join the website and to request that you will be able to join it. You will see the detailed links in the last slide. We have regular meetings and we are communicating on different channels to get here the sustainability assessment done. It's a collaborative ecosystem, and overall the position of SustainMobility is not a closed project right now. It's an open ecosystem, and we would like to integrate all expectations and engagements and different initiatives aligned, and we would like to share the goals. We had a high-level roadmap for the SustainMobility initiative ready since 2026, and we outlined the time frame to 2028. We have clear motivation and goals, and through that development with white papers and PAR at the end of project authorization request, we would like to enable the tools and all the benchmarks to get to a multi-year initiative and have at the end a systematic approach available as a roadmap to highlight sustainability needs. We started and we began by framing the problem and building a shared understanding. We then moved into a structured knowledge development through white papers, followed by the PAR request we started since some weeks ago. And finally, we are focusing on practical tools, benchmarking, and having that impact assessment in the real-world application available. The reference is in specific date, and we would like to have an active involving from other initiatives to be able to deliver the milestones and the deliverables. For the different stakeholders, it's clear that different outcome is expected, and we will go step by step, learning and refine our final result. What is the background and why do we need that? We ask simply an important question at the beginning. How many people in a city commute every day? What are the distances and how much material and energy are they using with what impact on the environment? Taking these together, we saw that today a lot of cities are still car-centric, and also the city planning is car-centric. So that leads to high emission, and if we only go on that systematic level that we would like to reduce emissions by driving less, that's not the possible solution. We need really coming here from a fragmented ad hoc solution to an overall structured and neutral framework to make it possible, allowing policymakers, industry, and cities to assess their impact, compare options, and make then informed decisions. Over that, we need not a single solution. We learned that we need an complete understanding and mobility transformation, and this on different ways to go. We explain that purpose of the initiative, and we go why do we that with a standardization. We see our initiative as a catalyst for a human-centric digital green transition in the mobility based on SDGs, as already mentioned, but as well on ESG requirements, environment, social government requirements to fulfill reportings in different ways. The transport sector is quite clear. It's responsible for roughly 20% of global CO2 emissions. So it's clear we need to reduce that based on a deliverable pragmatic approach. And that's our idea that we now go through that approach. using already existing standards, not starting from scratch, but then coming with the new needs of a measurable, transparent process, and then come to a real world outcome. Behind there is a conceptual architecture. We have the technical innovation and the social innovation that leads to the mobility transition. And focusing on the social innovation, it focuses on the context with governance, equity, accessibility, public acceptance, and at the end, an institutional framework. These factors determine whether technology can be accepted and can be deployed, scaled, and at the end, trusted. And for sure, the layer with mobility transition, it addresses and behavior change as well. So if we just want to have one person is changing, nothing really happened. So we need the sustainability, mobility as an technology, social structure, and behavior on aligned purpose. And we figured out that this reduced complexity, showing with a systematic perspective, that we see there is a standard, there are indicators, there is assessment in the back. And for here, we see based on that framework a multidisciplinary design, having experts from technology, policy, and social science or cities and industry as well in that impact assessment framework. We would like to invite also more to make that as at the end as a global framework. We launched some white papers in 2025. In August, we launched the first white paper. It was the key initiative as a statement, and we started with clear definition on taxonomy, what is electrification, what is shared mobility, zero emission vehicles, public transport, oriented development, and other things are here the key terms. We finalized it, it's public available, but that was only the first step. We are now, as the team and with the entire team, are working on the white paper 2. We would like to provide this white paper in April this year. We are going from the practical maturity model to an so-called SustainMobility maturity model. This includes a very pragmatical approach on including cities, transportation authorities, industrial partners into the systematic approach with the 5 pillars of dimensions: emission, equity, interoperability, resilience, and circularity. Bringing this under one umbrella is, in our eyes, the most efficient guideline to align with already existing standards. We are also here starting not from scratch, but we are looking to what standards are already available, and we adapt our model and put it based on these practical standards already, based with that clear pathway going forward. The white paper 2 shows in the end how sustainability mobility is possible from the vision into translated practical guidelines. With that practical guidelines, we are ready to go with the IEEE project authority request, or so-called PAR. This is the key step for us as the next point, and we can here find core elements as the basement for a standardization project with a clear scope, with a clear purpose and objectives. We then rather have the umbrella to work on a structured and accountable standard way to have at the end an overall all IEEE standard requirements. Then the last 2 slides, there is the benchmark standard and assessment tool. It's an already existing tool where we also step in and we use this umbrella for our initiative with the core pillars of transportation, health, and governance, and including environmental stuff, to bring it under our needs. So we defined a deliverable for us to have here, based on this initiative, a measurable, comparable, and actionable indicators as a result out of this existing tool. So then the last slide for today as a summary, we know that approximately 20% of the global CO2 emissions is coming from the traffic. There are several standards and regulations like ESG, SDG, and CSR requirements. In order to fulfill that in a very efficient way, emission-only reduction is not a key. We need a very holistic approach. This must be a standardized way. Therefore, we as IEEE are able to do that, and we can provide on reliable data and included cyber test beds. Here, really the essential move coming from assumption to a really impact assessment. And with that background and our work, we know the final message that we need to have here an urgent impact, because the CO2 emissions is on 20% of the transportation sector. So it's needed to conclude that. And we are happy to involve you with your experienced solutions into that activity. It's an open industry connection activity. To get involved, it's easy to use the link, and there is a form. State your name and your email, and then you will get involved in our activity. That was a short summary of our activity, and I'm happy to have the time left for some Q&A. Thank you so much.
Thank you also for this talk, and also for showing us which are the connections between the various societies and OUs of IEEE. I think our colleagues attending here and those who will be watching this video will certainly be attracted by these opportunities, collaboration opportunities. So thanks you also to you for your speech. Do we have questions for our speakers? I've not seen them in the chat, but if you want to switch your mic on and you want to ask questions, please feel free to do that. For the sake of time, I think we have time just for one or two questions.
Okay, I have a question about some points talk. So thank you for giving us the impressive speech. And you mentioned that for some tough tasks, you need more quantization bit, or some simple tasks we may need less quantization bit. So how do you evaluate the task? That is the first question. And the other question is that when you do the quantization, does it prolong the training time? Okay, thank you.
Yeah, sure. Yeah, that's a great question. So let me answer from the first question. So for the task, this is something we are still looking into. But we are actually looking into those agentic tasks. So when it comes to like agentic AI, there are some general classes of tasks, such as planning, tool calling, or execution, like terminal execution and writing up code. These are some general classes of tasks. And we find that generally planning is super, super important. This is where you want to focus a lot of your computational complexity, versus when you're actually executing, you're just following whatever plan that you have come up with in the beginning. So we are looking into those general classes of tasks rather than a very specific set of tasks, like say math, reasoning, or coding, or like common sense question, or those kind of things. So that's kind of the classes of tasks that we are trying to evaluate the difficulty on, and to elaborate on that further, we're not exactly looking at the difficulty, but we are actually looking at how sensitive how sensitive these tasks will be to the proper inference of the language model. To that end, we look at things like how sensitive these KB caches are that are generated on these specific time steps or according to these specific tasks. Does that answer your first question?
Oh, yes. Thank you. And about the second question, so
Yes.
when you do the quantization, I think it belongs to the dynamic quantization. Is that right? Okay. So
Yes.
does it prolong the training time?
Sorry, I didn't quite get what you mean
When
when you
you do the
say
training
yes.
of the AI model, so does it prolong the training time because you do the dynamic quantization? So if it
Yes.
does, how many percentage does it cost? Okay, thank you.
Oh, okay. Yeah. So in case of the multi-bit precision network training, because there are two overheads here. The first one is like what I mentioned before. We need to run multiple forward and backward passes for each of the quantized child models. So say you want to support 1-bit, 2-bit, 4-bit, and 8-bit. That's four additional child model on top of the FP32 parent model. So you'll need four more forward and backward passes. So the training time will be 4 times. This is one overhead. The second overhead is when you are trying to train these quantized network, you have to perform something called fake quantization. So this fake quantization also adds another overhead is trying to simulate the effect of the quantization in your GPUs, but using floating point number format. We still need the floating point number format because when you want to train your network, you have to compute the gradient and stuff like that. So you cannot do that in an integer. So you have to fake the quantization. So there's another overhead there. So I would say in total, it will be like 5 to 6 times more effort compared to just training the FP32 model. So that's why these kind of multi-bit precision networks or dynamic quantization networks, they couldn't scale to larger models. So that's why we wanted to make some efficient training methods for that. Yeah.
Okay, thank you. Thank you.
Yep. Thank you. Thank you
Thank
for great
you.
questions.
I think we have just time for a question to Mr. Pascal Master. Do you have questions? Otherwise, I'll ask one. Pascal, you talk about digital twins. I'm particularly interested in this topic. And you talk about like test bed, cyber physical test bed. So I call digital twin. So how much are these kind of models widespread? So are they available? So are you talking about this in your white paper? Are you addressing this topic?
Yes, not for the entire framework, but for example, for the batteries used at vehicles because of the European battery regulation. There is a clear standard how digital product passports and digital twins could be used. And we use this as an example in order to make it available in a standard way to scale later on. Yeah, but with these examples for battery, this is included in our project.
Okay. So I think that for the sake of time, we need to, thanks again, our speakers. I will put the recording online for those who weren't able to attend. Thanks again. I will get in touch anyway because I think your talk was very inspiring. And, I hope that you will be joining us for the next talk, which is planned at the end of April. Thanks to both the speakers, the officer, Dixon, for supporting always these talks. See you soon. Bye-bye.
Thank
Thank
you.
you.
Thank you.
Nice
Bye-bye.
talk. Thank you.
Thank you again.
Yeah.